Okay, in this part, we will talk about the interface charge and bias temperature instability. Interface charge and bias temperature instability are also the very important reliability challenge in the silicon-based device. Recently, not only in the silicon, but also for the advanced CMOS, wide bandgap semiconductor, emergent memory are all suffering the similar issues. So first, we need to understand the basic oxide property. So you can see from the band diagram, this is typical MOS structure band diagram. In the ideal oxide, we hope to have a defect free. That means there's no charge in the oxide, no allowed energy state in the forbidden band gap of oxide or silicon. We also hope to the oxide works as a perfect insulator. That means there's no carrier transport through the oxide. But in the real case, the defect and the allowed energy state are always exist at the interface or the bulk of the oxide. And several charge injection mechanisms actually are possible in the real oxide under the practical bias conditions. So we also need to understand that what are the possible charges and defects in oxide can be existed. And there are the 4 different charges. First one is a mobile charge, and second one is a fixed charge, and third one is the interface trap charge, and the fourth one is a box oxide trap charge. So this is a typical schematic to illustrate these 4 different charges here. So for example, this is a place where we might have the mobile ion charge, and this is a place we will have the boxide oxide charge, which can be either electron or hole trap that can be happen inside the silicon oxide dielectric. Or we can also have the fixed charges in the interface or the interface trap charges in between the silicon dioxide and silicon interface. So first, when we talk about interface charge, or sometimes we also call as the interface trap state, which is mainly the charges at the silicon dioxide silicon interface. So the origin can be structural defect, for example, dangling bond, or oxidation-induced defects. And the possible solution for the conventional silicon device is we can have the low temperature hydrogen annealing try to decrease the interface charge. And here is some more information related to the interface charge. This is a typical band diagram between the metal insulator and interface here. And the interface charge is mainly shown in this region here. So the energy level state existed in the forbidden band gap. So this is a forbidden band gap, but we actually have the allowed energy level state here. And there are 2 types of interface states. One is a acceptor-like state, and another one is a donor-like state. Acceptor-like state means that the state is neutral when empty, but the negative charge after the electron occupies the state. And the donor-like state means that the neutral when full, but the positive charge after the electron leaves the state. This schematic can be also illustrated in the right-hand side, where with a donor-like interface state or the acceptor-like state here. So as you can see here, under the neutral condition, when your Fermi level below the defect state actually is empty, so it's neutral without any charge. But when your Fermi energy is above your state, then this state can be charged with negative charges here. Another case for the donor-like state is that when our EF is below the energy state, and this state will exhibit as a positive charge. But when EF is above the state here, and then the state will become the neutral. And the second one is a box oxide trap charge. So it can be positive or negative charge in the box due to the trapping electron holes. So some possible origins, the damage generated during the process after the oxide grows, for example, the radiation or some charging effect during the plasma processing, or the defect generated during the operation, for example, the high field electrical stress, hard carrier injection, or even the radiation. Here is another schematic to illustrate the difference between the bulk oxide trap and also the interface trap here. So in the last two slides, when we talk about interface, there is mainly the trapping between the dielectric and then the interface. In here, we call this as a NIT here. But there's a possibility to have the defect inside the dielectric here. If the defect is really in the deeper dielectric, that's how we call this as a bulk trap defect. So electron trap and hole trap located away from silicon and silicon dioxide interface as shown here. This is a bulk oxide trap. And deep trap show large time constant for exchange of a charge with oxide bands. So the charge is almost fixed. This will affect on long-term stability. Permanent trap charge carrier can change device properties and long-term drift and eventually device failures here. And one more thing I want to mention is that in the region between the bulk trap charge and then the interface trap charge, there's a region here that can also be in trap. And this is what we call the border trap here. So the border trap is the trapping a little bit far away from interface, but it's close than the box oxide trap. And here is a summary of the charge injection in the metal insulated semiconductor interface. Conventionally, we can have the Schottky emission. This due to the once we under the typical bias, the carrier can gain some energy across this barrier here. And therefore, we can have the Schottky emission here. But sometimes we also have to consider once we have the defect in the dielectric. So if we have a defect dielectric, it can have the poor Frankel emission. So that means electron can first jump to this defect and then jump out defect to reach another side. Or if we have the too many defects in the dielectric, then we have the hopping conduction. So that means the electron can first to jump this one, jump to the second one, jump to the third one, in the end to reach to the other side. So that also will become the conduction mechanism. So as a summarize here, when apply high electric field to the electrode, carrier will obtain energy from heat. Therefore, it can cross the barrier. So that can lead to the Schottky emission. But some trap state or defect exists inside the insulator, and carrier has already been trapped in the specific state. And this can also help for the carrier injection through this defect. And if we have a high density defect, that can cause a hopping phenomenon. And on the other hand, another charge injection we should be careful about is, for example, the FN tunneling. This is mainly happen in the dielectric larger than 10 nanometer, or the direct tunneling. This is happen in the very thin dielectric. So in this case, tunneling has a stronger depends on applied field, but not related to the temperature. So here is a typical equation for the FN tunneling. And usually we'll plot as shown here. If we can plot in this way and give a straight line here, and that indicates that this current conduction mechanism follows the FN tunneling. And then we can also extrapolate the interface barrier phi-s here. And this is typical equation for the direct tunneling. So direct tunneling is mainly due to the quantum mechanical tunneling through the trapezoidal barrier between the two silicon conduction bands here. So you can see because the dielectric is too thin, so it's easily to have the quantum tunneling from left to the right here. So electron travel through the oxide, do not enter the oxide conduction band, and arrive with a high energy in the another side. And here is a typical experimental result in the case with a direct tunneling. And in the very thin dielectric with a 2.5 nanometer, you can see the lead current can reach very high. And if we try to compare with the different oxide thickness from the 36 angstrom to the 10 angstrom, and we can find out that the current, gate lead current is increased very fast here. So direct tunneling current at 1.5 volt increased by 10 orders of magnitude, for thickness decreased from 3.5 to the 1.5 nanometer. And that's why when we continue to do the oxide scaling, we need to have a high K dielectric to avoid the direct tunneling issues. And also, this is one of the experimental data shows that from the thicker dielectric to the thinner dielectric, and then the leakage current, actually the mechanism is a transition from the FN tunneling to the direct tunneling. So therefore, introduction of the high K dielectric becomes mandatory.